Hello, welcome back to another lecture on speech processing. So last class I had started this idea of sequential modeling. So what is that? That is, I have a sequence of data. So that's something that we are going to encounter, and speech is one example of that. There are many applications where the order in which events occur, etc. are important, right? You can't jumble the order, and therefore we have to, the order itself carries a lot of important information, right? So when I speak, right, and or when I write, right, the words have to be in a certain order. There's a grammar that tells you what word follows with what word with certain probability and so on, right? You can't just jumble the words and put. If I take a sentence, right, I can't just jumble the words in sentence and speak, right? That is, or write. It's not going to make any sense. So until I write the same words in the correct order, right, or that's the idea of, you get those jumbled letters and you're trying to ask to find out the word, right? Jumbled letters themselves are meaningless unless you have the letters in a proper, order, right? One after the other that make a word, right? A meaningful word in your vocabulary, correct? So, and same is true for weather, right? You want to know 5-day forecast. The next 5 days it will be sunny. I mean, it is sunny followed by rainy by cloudy. That's what I mean. If I say one of the days it will be rainy, one of the days it will be cloudy, one of the days it will be 2 days it will be sunny, and 1 day it will be cloudy. Now, which 2 days are cloudy, which 2 days are rainy? Those things are very important, correct? And so, therefore, the time ordering is informative and very important. I mean, that is what makes a lot of useful kind of idea, right? Stock markets, DNA sequencing, infinite text data processing, so many things, right? And therefore, we are going to start, and I'm going to review what we did last class so that you get some idea. So, we talked specifically about the case of weather prediction, right? So, how do I predict the weather, right? And so, we are going to introduce this concept of a Markov chain, and basically Markov chains depend. So an event depends on what happened in its history. So it can be long in history, 5 days in the 5 events in the history, 2 events in the history. But more often than not, in most applications, for simplicity of math and ease of implementation and so on, we worry about something called first order Markov chain. So the next event will only depend on the previous event, not what happened in the previous 2, not 2 in history or 3 in history or 4 in history, only the previous one, right? So that is usually a very common assumption. So it's called first order Markovian assumption. So in this case, we are trying to predict the weather. So the forecast for the next day will only depend on what happened today. So if today was sunny, that is all that I need to know. I don't need to know whether so today was sunny, yesterday was cloudy, the day before yesterday was rainy. All these 3 pieces of information might be useful for me to predict tomorrow's weather. But more often than not, we only assume the first order Markovian process because of, as I said, ease of implementation, tractability, mathematical tractability, and so on, so on, so on. So we are going to only say that today's weather, I don't care whether yesterday was cloudy or day before yesterday was rainy. What happened today? Today's weather is only going to determine tomorrow's weather. So tomorrow's weather is only dependent on what happened today. It does not matter what happened yesterday or day before yesterday. Okay, so that is the first order. If it depends on the previous 2 days, all the 3 days, then it becomes third order Markovian. Or if it's depending on the previous 2 days, it's second order, right? So we can have, but we normally use only a first order process. Okay, so what do we mean? So we'll start introducing this concept of a state. A state is basically, so we are going to define the problem well. Okay, so for example, if I'm talking about the weather condition, we assume that the weather is either rainy or sunny or cloudy, only these 3 states. So it remains in one of these 3 conditions only. Okay, so on any given day, it can only be cloudy, or it can only be rainy, or it can only be sunny. That's the way we are going to define the problem. Okay, so therefore on any given day, it can either be sunny or cloudy or rainy. So it can be in any one of the 3 states. That is the term we are going to use. It will be in one of these conditions, one of these 3 states. Okay, so the term state is going to be used, and in our case, the state can either be a state of being in sunny, or the state being cloudy, or the state being rainy. So we are assuming there are only 3 possible weather conditions on any given day. Okay, and during the whole day, it's going to remain in that state. Okay, so Now, what we are interested is like, as you and I, why do we look at the weather and all that, right? Is it, what is the 5-day forecast? Oh, I am going to Mysore. I am going to, whatever it is, Kaziranga National Park. Is it going to rain for the next 5 days? Oh, my trip is ruined. We always want to know what is the forecast for the next 5 days, right? Or 3 days, or what is at least tomorrow's forecast, right? So these are useful. I mean, everyday sort of scenarios that we encounter, right? So how do we go about doing it? The weather prediction is a very, very difficult problem, but I'm just using that as a flavor to sort of introduce this idea of Markov process, Markovian chains, and then we'll talk about the hidden Markov model, and then how it gets applied to speech. And speech is one of the many applications. It's the same idea sort of goes into, for example, stock market prediction, right? So a lot of the speech engineers in the 1990s, because they were the best guys in hidden Markov models, were actually taken over, paid heavily and bought over by Wall Street firms, right? So Markov, the HMM aspects were very, very important in the 90s for many other applications, including stock market, right? And today, even today, many of you engineers end up being, or scientists, research, anyone, a lot of you end up being in investment banking and so on. So because a lot of these skills, these math skills, get applied in many, many different areas. Okay, so I can ask, a thing like, what would be the next 3-day forecast or something, right? So as I said, to do that, I need to have some historical information. I need to know the ground truth so that I can build a model. In other words, I want to find out what happened historically, and I assume that whatever patterns occurred in the history, that would help me in the future predict properly. Okay, so if the same sort of pattern continues, and we are hoping that the model does not change, or the patterns do not change with time, right? So the stationarity assumptions are being made here. Then hopefully the same model will help me predict something in the future also. Okay. So what do? I look at historical data, right? I can look for the last 100 years, right? People have started recording weather conditions, weather temperatures, everything for the last 100, 200 years. We have a lot of actual data that is provided. Okay. So since these data are already available, right, I can actually use that data and even see how good my model is for that data by actually seeing what happened and then how often. For example, we are only talking about first order Markovian process, right? So how often when something was cloudy, the next day happened to be sunny, right? Or how often when the thing was sunny, next day it turned out to be rainy. So the way we do is we look at the historical data. We are only recording some, I don't know, some 10 or 12 days, but the more data we have, these are all data driven approaches. The more data we have, the more large historical kind of data we have, the better our model is going to be. Okay. So in this case, we have sunny, cloudy, rainy, sunny, cloudy, some weather pattern we observe. And we are going to say, let us calculate the probability of today being sunny given that yesterday was cloudy. Now, how do I compute this probability? So, I am going to try to find out the probability given this historical data. What is the probability of today being sunny given that yesterday was cloudy? Okay. Or in a given on any given day it was sunny, on any given day if it's cloudy, what is the probability of the next day being sunny? Because we are assuming that it's stationary, so it holds irrespective of whichever day I'm talking about. Okay. So how do I compute this probability? This is actually some sort of a Bayesian thing that you have to kick in, right? So it's probability of sunny given it is cloudy. So probability of sunny given cloudy is nothing but probability of cloudy and sunny, that's the joint probability, divided by the probability of cloudy, right? And that, we can use a count method of probability. How many times was it cloudy, right? Or what proportion of times was it cloudy? And among those proportion of times that is cloudy, how many days did it follow with sunny? That becomes the numerator, right? So what is the probability of today being sunny given that yesterday was cloudy? How do I do that? I found out whenever how many times cloudy was followed by sunny, because given yesterday was cloudy, the next day was sunny, right? So given cloudy, here there's one case sunny, this cloudy, right? So only one case of sunny is following cloudy. Okay. and how many times did cloudy itself. So, denominators, remember, joint probability of A given B is probability of A intersection B divided by probability of B, right. Now, the denominator is only, so here probability of sunny given cloudy is probability of sunny intersection cloudy, that is cloudy followed by sunny or sunny followed by cloudy, sorry, divided by probability of cloudy, right. Probability of sunny following cloudy, only one occurrence out of the number of, so 1 divided by n, let us say that n we can keep it like n itself. The denominator is how many times probability of cloudy itself. So, number of cloudy again count by n. So, number of cloudy is 1, 2, 3, 4. So, only sunny following cloudy was only 1 and there were 4 such cloudy events. So, 1 by 4. So, this is going to be 0.25. See, given yesterday was sunny, cloudy, it can either go to a sunny condition or state or cloudy itself or rainy itself. So, it can go to only one of these 3 conditions. Given cloudy on one day, it can go to sunny or cloudy or rainy. So, there are only 3 conditions and given the state, it can go to only one of these 3. So, this total, since it has to go to any one of these 3, the total should add up to 1, right. That is something you should, you can, common sense tells you. Now, I already found out probability of cloudy given probability of sunny given cloudy is 0.25. This is the one. Now, what is the probability of cloudy going to cloudy again? So, I find out that probability of cloudy given cloudy is probability of cloudy intersection cloudy divided by probability of cloudy. So, the denominator is again probability of cloudy. There are 4 such events. Now, how many times cloudy is followed by cloudy? This is the only case, right. So, cloudy followed by cloudy is again 1. So, you will get 1 by 4, that is 0.25. Okay. So, now I already covered 2 conditions, probability of cloudy, the next state being sunny, that is 0.25, or the next state being cloudy, that is 0.25. So, 0.25 plus 0.25 is 0.5. So, total has to add up to 1. So, this should be 0.5 and we can double check that. So, how often is the probability of rainy given cloudy? That is the only condition remaining. So, the denominator again is 4 because 4 cloudy conditions, but you see rainy following cloudy is 1, rainy following cloudy is another one. So, the 2. So, 2 by 4 is 0.5, half, and that we expected, right. So, this is the way we are going to use historical data to find out all these probabilities. So, how many different probabilities I have to calculate? So, given cloudy, I can probability of sunny given cloudy, probability of cloudy given cloudy, probability of rainy given cloudy. So, 3 over. Now, I change that. Sunny, probability of sunny given sunny, 1, probability of cloudy given sunny, probability of rainy given sunny. So, 2 over. So, 3 plus 3 6. Then for a final condition is rainy, and again rainy to sunny, rainy to cloudy, rainy to another 3. So, 3 cross 3, 9 such probabilities I have to find. This we will put in a matrix form, right, and that is called a transition matrix. So, therefore, when you are going from any given state to any given state, this is called an ergodic process, right. It can follow any one of the conditions, can go to any one of the other conditions. So, sunny can go to sunny itself or rainy or cloudy, right. It can go to any one of the conditions. Similarly, cloudy itself can go to rainy or cloudy or sunny. So, it can go to any condition to any condition. So, if you look at this and what do you do? We looked at the historical data, and so there are n squared such probabilities. Given sunny, I can become sunny next day or cloudy next day or rainy the next day. So, given sunny, today can be only one of these 3 weather conditions. Therefore, this total probability should always add up to 1. So, 0.25 plus 0.5 is 0.75 plus 0.25 is 1. Okay. Given yesterday is cloudy, today can be only one of these 3. Again, it will add up to 1. Given yesterday was rainy, you find, how do I find this probability? So, historically, I look at all weather conditions, number of days it was rainy, that is the denominator. Numerator will be, if I am trying to find sunny given rainy, number of times sunny followed rainy, right, and that will give the proportion, or cloudy followed rainy or rainy followed rainy, and again I get this, right. So, this is a transition matrix. Since I had 3 states, 3 into 3, 9 such things will come. If I have a 4 state process, it can go to any one of the 4 states. So, 4 cross 4, 16 transition probabilities. 5 states, 100 states means 100 cross 100, right. So, that is the way you create this transition matrices, okay. And you can pictorially represent this in terms of these states, or the circles and these arcs or edges, okay. So, this is called basically a state diagram. So, you basically can represent this whole matrix in terms of these circles and arcs and so on, or what we call the states or nodes and arcs, nodes and edges, whatever you prefer to call them. Many terms, they are used in many scenarios, and the terminologies can be slightly different, but the ideas continue to be same, okay. So, for example, if I draw pictorially, this is a rainy condition, right, and this is a rainy state, this is a cloudy state, and this is the rainy state. So, there is a sunny state, there is a cloudy state, and there is a rainy state. Now, this picture captures everything. From sunny, the probability of being back in a sunny state is 0.25, and that is what this matrix is showing, right. From sunny going to a cloudy state is 0.5. See, the arrow is going from sunny to cloudy. So, from sunny to cloudy is 0.5, and from sunny to rainy is 0.25. So, the sunny to rainy, the arrow is in this direction, going to rainy is 0.25. So, you can see that from this sunny state, 3 arrows emanate, they come out of this. So, one going towards rainy, one going towards cloudy, and one going towards sunny itself, okay. And so, this comes out and goes here in this case. In these case, it comes out of these 2 states and goes to another state, okay. Similarly, from another state, things can come. So, from sunny, arrow here back to sunny, from rainy, an arrow comes back to sunny, from cloudy, an arrow comes back to sunny. So, there are inputs also, right, I mean, or in this direction. So, what does this mean? Given something is cloudy, the probability that it will become sunny the next day is 0.25. Given something is cloudy, the probability the next day will become sunny is 0.25, okay. That is what we are capturing here. Or given that it is rainy, probability the next day will be sunny is 0.5, right? See, it is going in this direction. So, given it is rainy, probability it is going to sunny is 0.5. Or if I want to talk about rainy to cloudy, given it is rainy, the probability next day will be cloudy is 0.25. Given it is rainy, probability the next day is cloudy is 0.25, okay. So, we can represent this information in either the matrix form or in the form of these diagrams, state diagrams, okay. So, these are called the states, the sunny state, the cloudy state, and the rainy state, and this is the probability that going from sunny one day, the next day being rainy is 0.25. Probability of being in cloudy and the next day going to rainy is 0.5. Cloudy, next day rainy is 0.5. Okay. So, normally the we call these states as I, J, K and so on, and if I am going from the ith state to the jth state, so these transition probabilities, we use the small letter a with the subscript ij going from ith state to jth state, or or sometimes we say going from jth state to ith state, so ij, depending on the conventions, different, I mean the standard 2 conventions, obviously only 2 ways, depends how we deal with some. In some scenarios, they talk from I to j, j to I, whatever it is, okay. So, as long as you are clear, the aij is the transition probability. This is actually a probability going from the ith to the jth state. So, there will be 9 entries in the 3 cross 3 matrix, 16 if you are talking about 4 states, or 10,000, 100 cross 100 if you are talking about 100 states, okay. So, still it is what is called not a hidden, it is visible, okay. The hidden, there is no hidden part here, this is a proper Markov chain, okay. Now, so if why am I doing this? After historically getting this data, I can predict to a very good extent what if this model is true, that whatever I historically observed, it will continue for the next few days, right. It is not going to abruptly change whatever is happening, right. We assume some stationarity here. Then I should be able to make a very good guess of what the next 5-day forecast will be. Okay, so this is a very, very simple minded approach. Obviously, weather prediction is a very, very difficult problem. Okay, there are lots of parameters, there are lots of conditions that you have to worry about to predict it properly, right? The model itself is much, much more complicated. I am only giving a simple scenario for you to see how by using the idea of weather prediction, I'm trying to get you to do something in speech. Okay, and that's why I'm trying to use this example, because something that you can relate or at least visualize very easily. So the question that I'm going to ask is, given the state transition matrix, this is something that we have observed over like 100 years of historical weather data, or 10 years, or last 1 year, whatever it is, somewhere I'm able to get this data, and the more data we have, usually the better our estimates of these values are. Okay, so this is called the transition probability. Okay, now after I get this matrix, now I'm asking, I don't know, I can't look into the future, so I'm asking, what is the probability that given that yesterday was cloudy, or or today is cloudy, whatever it is, I have observed already. What is the probability that the next 5 days is sunny, sunny, cloudy, rainy, cloudy? Remember, I have still not, these weather conditions have still not occurred. This is a prediction, right? Only thing we know is yesterday was cloudy, because we are only assuming first order Markovian. So what happened in just the previous event is more than enough. That's what we have been telling from beginning, right? Not what happened the last 5 days, before the prediction starts. So let us say yesterday was yesterday night, this is what I was doing. I had the idea that I know that yesterday was cloudy. Now I'm going to ask, like, next 5 days, sunny, sunny, cloudy, rainy, cloudy, right? What is this? I still don't know the truth, right? This is now predicting, right? And the question, what is the importance of this? I should predict properly, right? If I don't predict properly, people are not going to be, take me seriously. Hey, this guy always gives some junk weather prediction. I'm not even going to bother looking at it, right? So you want your weather prediction to be as accurate as possible. We are going to make mistakes, right? You can see in everyday life also, the IMD, the Indian Meteorological Department, will say something. Sometimes, often they are good. So often they are correct, but sometimes they do make mistakes, right? And so this is never 100% correct answer, right? There's always some mistake we're going to make in all of these methods. The whole idea is to reduce the number of errors we make. Okay, we're always going to make mistakes, no doubt about that. Okay. The question is, a good system will make very little, few errors. That's all it will do, right? And so that's how we can compare systems. One that makes less errors, obviously a better system, right? And of course, things like compute and all these things, how much time does it take to come up with this prediction? Can it do? All these things also matter, okay? So now, if I want to predict the probability of sunny, cloudy, rainy, cloudy, given that the previous condition is cloudy, is very simple once I have this transition matrix. So given that it's cloudy, the next day has to be sunny. So I have to say, given cloudy, the next day is sunny. Given cloudy, next day is sunny is 0.25. Then the next day we are saying should be sunny. That means, remember, we are only talking about first order Markovian process. So the previous day was already sunny. Now I don't worry about the cloudy. That happened 2 days back, right? So the previous day was only sunny. That's all I care about. It's a first order process assumption. So sunny given sunny, that's what I have to multiply here, and that is sunny given sunny is again 0.25. Then cloudy given sunny, that is cloudy given sunny, given, right? Cloudy given sunny is 0.5, rainy given cloudy. So given cloudy, rainy is 0.5, so another 0.5 comes, and finally cloudy given rainy, so that is 0.25. So this is the probability according to our model, right? According to our model, this is the probability of the observation sunny, sunny, cloudy, rainy, cloudy. Okay. So now, if I want to say what is my best prediction, so this is a 5-day forecast. To predict the next 5 days, how am I going to predict the next 5 days? I know that the probability of observing sunny, cloudy, rainy, cloudy is this probability. Like that, I can find for all combinations of these 5-day forecasts, right? I'll come to how many combinations there are, and for each one of them, I can compute the probability. And once I compute the probability, I look at the one that has a maximum probability. Okay, that is my best guess of a 5-day forecast, because that has the highest probability given the model that I have already looked at historically from the data. This is the most likely, highest probability it has, right? So therefore, I have to look at all possible 5-day forecasts. So I can say sunny, sunny, cloudy, rainy, cloudy, sunny, sunny, cloudy, rainy, sunny, 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 cloudy, rainy, rainy, whatever it is. So many conditions will come. So we'll see easily how to calculate that. And given that that is there, I'll calculate the probability for each one of them and then find the max, and that will be my best 5-day forecast. Okay, so we are going to now deal with that problem.